Hello, Thomas.
Hey, Luca, how was your
Hey,
week?
my week was busy, but I got new glasses because the old ones, yeah, it's a fun story. Um, the old ones were done in emergency because I lost my previous ones, and so I got ones that were too strong for me. And so then my wife convinced me to get red ones. So now I'm sporting red glasses for the foreseeable future.
That's pretty smart. Uh, yeah,
All right.
well,
Where are we? Where are we? So the last time, I think we had a lot of insight looking at the individual kernels, right? For the Liger kernels, but there's still one, and we got faster. So Liger plus Thunder, it's actually faster than all the combinations, except for one kernel that we quite don't understand. And it's fascinating because we have an opportunity now to exercise the various features for Thunder um, to get insight on the computation. And so, yeah, what's next? We need to dive into that one. So,
right. And so the kernel was the fused linear cross entropy. And so
yep,
this actually happens if you think about the model, you had the embedding, then you have the transformer blocks, and then you have the output layer and the cross entropy loss. And so it actually happens outside the transformer layers. And
yep,
so what we did last time was we like cut away all the transformer layers in order to have a more minimal thing. Um,
yep.
and then we want to run that through the PyTorch profiler and see where it takes us, right?
Yeah, yeah. Yeah, we don't know the solution. And so we're kind
Yeah.
of
So
discovering
I
things
was
as
on
we go.
I was on vacation last week, so I'm starting my week just as much as I'm finishing it. But yeah, obviously, this hour of the week is fun, even if you're on vacation. Um,
Yeah,
so
appreciate you being here, of course. Yeah, so let's get into it. Let's see this
yeah,
linear
let's
cross
hope
entropy.
they. So 5 minutes before we started, literally 5 minutes, my internet connection went out actually from the telco. And so if that happens again,
Thank you, Taku.
Luca will take over. Um,
Absolutely.
but yeah, so let me share my window, and you already know kind of how it goes. Um, we have this notebook. Uh, yeah, I always have it set up so that the dialogue for sharing the screen actually doesn't fit on the screen. The confirm button is off the screen. But okay, yeah, I
Yeah,
think we can
nice.
see it now.
Yep.
Um, and it's still running through all of the head things. And one of the things we did last time, and I didn't change anything, I just reopened it. One thing we did last time, we had a debug print in here. Let's get rid of that.
Maybe it was larger, like the font was a bit zoomed in last time, or was it the same? Because I
Yeah,
changed glasses, so I don't know. Is it the
yeah,
same?
it's the new glasses. I should have
Yeah, that's
everything.
hilarious. All right,
I should have everything in
perfect.
pink now, right? For the glasses. Um, there's there's actually there's uh, obviously Thomas Mann, a famous German writer. Um, and so he wrote The Magic Mountain, a thing. And my hypothesis is you should stop reading that after the first half. So there is a chapter called Walpurgisnacht, which is like the night to the 1st of May, where the witches dance traditionally, or people believe that. And a few sections after that, in the next chapter, there's they bought glasses, red and green and blue, also for the eyes, but mainly for the soul. And so at that point, you can put the book away. There's nothing much coming afterwards. Incidentally, then there's two philosophers. One of them is Italian, the more sympathetic one, I should say. But yeah, so so much for literature and philosophy. So I still need to rerun the thing that had the debug print before. So let me find this. The fused linear cross entropy. This was that. Okay, so now we should be able to measure things without it printing things all the time. So here we see it was 21 seconds with the fused linear cross entropy, and this is like without the with the forward and backward, and it's only 8 milliseconds when you do it without the fused linear cross entropy. And so obviously we want to see what's going on there. One thing we do here still is that we have the movement to CUDA all the time. And so we can take this out for the profiling. And so let's try that. So what's going on here? Device, oh, I forgot to have the .CUDA here. Okay, so we have the key averages that we discussed a couple of times now. We will have the same key averages here. And now you know why I made this small.
Yeah.
But so I'll make it bigger again. So in a sec. So what we saw here is that we have some very expensive addition matrix multiplication, and this is kind of expensive. And then the next most expensive thing here in the CUDA is a single matmul. This is also quite expensive. And then there's some cheaper things like there's an addition that comes from the backward, I think. And that's actually the most expensive thing here, right? So so we want to understand this better. But so right now we see that there's a lot of kernels, and obviously there's still too much going on to really say what is what. One thing we can, of course, do is we can get us the traces. And so we could do here Thunder last traces of the model default exec and get the last one. And we see that here, okay, we have the embedding and we have a slice and squeeze thing. And then we have the Liger RMS norm and the Liger fused cross entropy linear. And if we do this with the non FLC kernel, we can Thunder last traces model no FLCE -1. We see that this has a few NV fusions here. It also has the embedding, just as the other thing. So this is run identically. Then there's the Liger RMS norm, which is also similar to before. And then there's a plane linear here that's apparently much faster, even though the cross entropy is here afterwards. And so we want to map these kernels somehow to what's going on. And so the thing to do here is to get actually the timeline of what's going on the computer, right?
Yeah.
And so the nice thing is that the output of the thing that Thunder actually runs is just a Python function, so we can instruct the PyTorch profiler to capture the stack too, and then we can instruct it to save the trace.
In which case, there's some aliasing of terminology, right?
So
the trace the profiler is the trace that goes into something that we can visualize, whereas the trace for us is what we know very well from several episodes. So the Chrome trace, because Chrome, the Chrome browser can be used to visualize the execution, as we will see in a second.
So I will call this timeline with F fused linear cross entropy. And this will be one of them, and the other will be then the timeline with no fused linear cross entropy. And now I will load this into the window, and it's kind of a weird thing to do this way, but I guess it works. So I'm going to the developer tools in Chrome, and then I upload the thing. And now I forgot one thing, because we're working on the cloud. We need to download the timelines, right?
Yeah, we can make it more natural in the future. Everything is in Chrome anyway, more or less.
Yeah, we could just show it in the studio, right?
Exactly. Yeah, there's actually a visualizer for Chrome traces that is a reusable component.
Yeah, that would be awesome to have as a file viewer in the Jupyter notebooks, right?
Yeah, there's I can't remember the name of it, but yeah. No, it's not Presto. Anyway, whatever.
Okay. So we see here there's a lot going on, so let's unpack that a bit. So there's the PyTorch main thread that we have. There's a number of other threads. There's the PyTorch autograph thread, which apparently is here during the green thing. My hypothesis would be this would be the backward, likely.
These are actual Python threads.
So these are actual Python threads. And then there's stream number 7. And these are this is the actual GPU stream, right? It says Python, I think, because it's the process Python. But so you see here that these are the native vectorized element kernel. So we have this here. And now we would like to zoom out a bit, but this is probably not that easy, right? Oh yes, so this was the total, and we can zoom in. We could, the first thing we could try to do is like see if the forward or the backward is bothering us more. I'm thinking that the forward is bad enough, so we should look at the forward first. And there we can see that there's, can we go into the Python main thread? And so there's forward with hello. Okay. There's the fused linear cross entropy forward. And so here we see that this is the Liger ops function. And here we can see what it does. It calls a number of things. So it calls the built-in method item of the tensor object, which is not a good thing because this introduces a synchronization point in all things. And then it uses the add method. And so I'm speculating here, but I'm guessing
Which was the one that was the slowest, right? I mean, which was the op that took more time, you know?
This is what took more time, right? So it might use the add because it tries to say, or it does save memory by using the input tensor as a buffer for pre-computing the gradient.
Yeah.
So you would only need one buffer for that. But so we see that there's another item call, and then there's some more add and another item call. And so I think these item calls are kind of not so good. And also the add well, we probably don't see what's going on at the kernel level here. And I wonder if we can, I can just scroll down and the upper things.
So the item call looks like they're like chunking the loss multiple times, right? And adding the actual scalar.
Right. And obviously, one of the things we did was that we took the original example, and I do trust them that I saw a good speed up there. But what we did is in the example that we took from the Liger repository, there was a masking of the targets. That meant that only one time step for each batch item was relevant. And the original example just took everything and masked the loss. And what we did was just cut out and just compute the linear for this last part. And I'm guessing that we're using the fused cross entropy linear for very small inputs relative to what they expected to see. And so very likely it's optimized for that. And we can see that here, and this is maybe also an important thing, well, we see here that it's calling the item method of the tensor, which I said causes the synchronization point, and you can see CUDA stream synchronized here. The main thing about the item is not as much like getting the actual item, but what happens is that it has scheduled a gem and then a kgem K1 kernel, which is, I think, a split K thing. And then it does a GEVMX kernel. And so these are all from the matmul, but they show up under the item in the Python trace because of the asynchronous nature and the synchronization point from the item. And so what we see here is that it calls a lot of gem kernels for like quite a while, and we saw it in the summary that this is actually calling all these gem calls, like the gem 1k, and here the gem vx, and the ampere bf16 gem. And so all these calls are within the fused linear cross entropy. And we discussed this quite a bit, like what we should avoid, what we should do. And clearly for the problem size we're having that many kernel calls likely is just inefficient. And if we open the other timeline, I don't think I can easily like keep two of them open. So if we open this one, we see the stream doesn't do much, but then there's like one bake, and let's see where this happens. So we have oh, this is already in the backward. So let's I think it kept something of the zoom from the crypt thing, right? And also it's not the PyTorch main thread anymore. Okay, so we see here that it has run fused kernel, which is the thing that MVFuser does, I guess. And this calls A10 zeros a lot, which also, is interesting. But so we have the 18 linear here, and we have the fused kernel that will be the cross entropy thing, very likely. And then the take along dim, I think these three are the cross entropy. And all these are launched while it has this one large cutlass call, which is, and we see it has WMMA in it. So it's a tensor core based matrix multiplication routine. And Cutlass obviously is the library enabling custom matrix multiplication like things from NVIDIA, right? And so we have that this is going on, and basically this is the main thing, but it is a lot faster than all these separate calls that we do for the thing. But also here we see that like at the very end, the linear does some like administrative stuff, and then at the very end of the matmul, it calls CUDA launch kernel, and then the kernel starts and runs until here, where for the autograd to move to the backward, it needs to be, well, it doesn't actually need to be done, and you see that it's overlapping that.
Some leftovers.
Yeah.
Yeah, it's very fascinating, like the power of fusing everything together, and so it just runs. So yeah, in order to beat this, one hypothesis is that we are operating on shapes that do not favor the Liger kernel in general. And by the way, it's totally fine to leave the job to MVFuser, right?
Right.
In this case. But is it a realistic case? That's the question.
Well, yeah. So one thing we did here is, so if we look at the GPU RAM, we see that we're only using 6 gigabytes of the 48 that we have on the L40 GPUs, which are like my favorite GPUs because they're kind of, if I look at the matrix, they're the best value for the money, right?
Absolutely. They're awesome.
Yeah. And so one thing we should do is increase the batch size by a lot. And so one thing we might do, just for the fun of it, we might take the kernel and annotate it with, take the Thunder trace now, like this one, and annotate it with all the shapes that go in. If we have the hypothesis that there's a shape thing going on. So that's happily our colleagues wrote a thing for this. And so if I go back up where I call thunder.jit, and so happily our colleagues wrote a transform that does this for us. So from Thunder dev utils debug transform import, and I think it's debug execution trace. But yeah, let me
check it out. Okay, sure.
So there is a thing here going on where my personal vision for Thunder would be to have everything packaged up as a transform. And so if we look at the debug, is it debug transform?
It's called, debug transform. Debug execution trace returns a debug transform.
Okay, so debug execution trace, it has the pre and post callbacks. I thought that it had there must be another thing here. So yeah, read the source code of your thing while you're already live. So the create debug bone symbol, and we want that, right? And so that is the default here? So debug execution trace, post callback, none, no. Okay, so
so there's, go ahead, sorry.
So I think we want to call this as the pre-execution thing, right? But I thought there was a utility function for that too. Do you remember?
Yeah, that's what I remember too. So that's what I'm looking for right now.
F pre-calling. Maybe it's under dev utils directly. Or maybe I have an old version of Thunder installed. Shame on me.
No, I think what you're looking at is correct. I'm looking at the notebooks.
Yeah, we should have a phone joker, right? Ask Shidich.
Exactly.
So
set debug option.
And I think it should be debug execution trace, but and so let's have it as a pre-callback the Thunder dev utils. And you see, this looks like there must be a better way to do it. And
exactly, yeah, this is one of those occasions where we realize there's a missing bit for developer
not
pleasantness.
All right.
Yeah, there's no such thing.
So
debug execution trace, we need to pass the callback, and the callback needs to be passed, and we have no predefined callback, which is weird. Yeah, okay.
Well, but so okay, let me open the file just so Lightning Thunder.
So pre-callback takes bsim and then whatever arguments in qargs.
Yeah, but why does it? But how do I call it?
You pass it to debug transform or to debug execution trace. Unless you don't have the latest, right? But it looks like you need to create a debug execution trace, which will return the transform. So you call debug execution trace as a function, and then you pass pre-callback equals and the callable. And that returns a transform that you need to add among the transforms, right?
Yeah,
that thing.
But so I should be doing the same thing here, right? So the question is, what does it call? So it calls this with 3 arguments, supposedly.
Yep.
And so,
which are the symbol and the
yeah, but now it says that
extra args.
called with 8 positional arguments, debug pre-embedding 1. Maybe it should be the post, right?
Yeah, I don't think the create debug bound symbol is something you should use there necessarily. This is more the
Oh, yeah.
Yeah, it's not the callback. You need to define the callback, and then that function will be used elsewhere.
But there was
in the
one
post.
that did that readily for me, right?
Yeah, that's what I remember too, but I can't find it right now. So we can just
Okay.
just
So
print.
next time,
Have a callable that prints. No. I mean, if you make a callable that takes a bsim, args, and quarks, and then just print that, I think it's good. I don't know.
Okay, yeah. Let's do that. So okay, so so it takes a bsim,
Yep,
args, and quarks.
And then args, star args, and star quarks. Yeah.
Right. So let's just print all of it. Well, let's just print. Oh yeah, let's print args. Yeah, just the first. And let's try what happens if we do this. Okay.
Yeah, we're definitely missing a something here.
Yeah, this should be. And oh, I know what happens. I should return this and then now I remember. So so we are supposed to return a string, and let's make a t.shape for t and args if is instance PyTorch tensor. And so what happens is that the debug, and this is very nifty, the debug trace, the debug callback will return a string, and then this will get inserted into the trace by pure magic, unless you forget to call the executor, I guess. Model default exit. Do I need another executor for it? I think I might want the different order, but probably not just that, right? No, debug pre-torch is not defined. Oh, it's in the backward. Then let's run it without the backward.
Yeah, I think so.
Python replay stack is empty. Yeah, so the profiler also doesn't like the debug transform, but we're getting there.
Yeah.
Bit by bit. So here we have it. And so what we did here is for all the operations, we have like a comment that gives us the shape of all the tensors. So if we look here, our fused cross-linear entropy is given a sequence length a 4 times feature size cross entropy feature vector. So 4 is the batch size, and 2048 is the feature size. It gets the weight matrix, and it gets the targets. And so usually there was another sequence dimension in here that would have made this 4 dimension much longer. And I would venture if we now send like much larger inputs through it, then it would fare much better. And obviously, one of the purposes of Liger is not only to make things fast, but also to make things save memory. So here you have it.
That's great. Yep. So anyway, the debug thing annotates things in the trace, and I think annotation is one of the values here. And some compilers also downstream would benefit from annotations. So annotations is something that we will probably work on in the future further.
Yeah.
So do we want to try with much larger and see how?
Yeah. So in order to do that, let me add to our cool debug transform. Let me also add the D-type.
Oh yeah.
So and I think we can kind of try to fake the values. And so what do we have here? The Liger fused entropy, Liger fused cross entropy forward with
bfloat 16 and int64,
and then a bunch of other things. And so we copy this to a new cell. And so if we...
I mean, it's actually great. What we're doing is like getting into the guts of the computation and kind of uncovering shapes and D-types of intermediates very easily in the end.
Right.
So the beauty of this is that it lets us analyze what's going on bit by bit and figure things out incrementally. I think that's pretty nice without all the fighting against anything else. We had just have it there.
Right.
So let's see.
So the first thing is to have the inputs. Yep. Then there's the weight. And that is, yeah, we can also use random normal there. And then the third thing is the targets. And I'm just going to use torch.ones and 4 and the D-type is torch int64. And now we have these 3, and we can just call this this function, right? Because it's just a function into weight targets. Oh, it's the symbol, so we need to call the implementation, which is now how do I get the... Yeah, let me just look up the kernel name. Oh, I think we made an implementation function because we so Liger fuse cross entropy
forward, right?
Well, I need to look it up. painful to the eye to do all the scrolling, but
Yeah,
so
no
forward
worries.
with hello it was called. That
Oh
was
no.
funny forward with hello also in the Chrome trace, right?
See
Because
the
I had a
effect
debug
of
print in there.
accumulating debt
Right.
bites you back invariably.
Maybe
Yeah.
I need to clean it up before the next session. But so, okay, we can call this directly, and we can, of course, do torch CUDA synchronize afterwards. And we can time it. Oh, it's double typed, right? And we can compare it to like torch logit is torch and then linear. And then loss is torch and then, and this is not quite fair because we're not doing the backward. And so, but to get the taste, torch and then functional cross entropy. And so I think it has more or less the same targets instead, but with a different ordering. So ignore index is -100 and reduction to mean. And so if we time this, it should be faster, and it's much faster. And one thing is that it's missing the backward. And so let's just do, we need to add requires grad equals true. Okay, so now it doesn't like this. And
Oh yeah.
but so to make this more even, let's do grad is torch autograd grad of loss with respect to int and weight. And so this should be like a fair comparison, if not a bit unfair to the faster method. And so now we can like scale up the sizes. So let's do 64 instead. And we see that, well, it gets slower as expected. Oh, but it's still
it probably diverges even more.
Right. And so yeah, so but did this like stay? No, it didn't stay the same, right?
It kind of did though. No?
I don't know. Let's try some larger number. So 2 to the 9, 2 to the 8, 2 to the 9. Let's do 2 to the 12.
Oh wow.
So I mean, obviously, if I have a substantial sequence length and And so if we
Yeah.
look at
They're
the
getting closer, right? Yeah.
now it's getting closer. And if we
Yeah.
look
It's half though, still half.
at the Liger kernel, if we look at the repository, we see that they say, well, yeah, the speed up happens with large batch sizes. So with large sequence lengths. So if you have a batch size of 4 and a sequence length of 1024, this is this. But if we now go to 16 maybe, then we're really in the kind of ballpark where they want to work with, and we see it's out of memory, just like
Yeah.
they predicted.
Yeah.
so
Yeah.
so I guess we're getting fair here. But let's
Yep.
try with a smaller one then. But I'm not sure that we recover from the out of memory quite well. Yeah, it's still out of memory. So let me try to if I get this forward with hello, replace it by the plain call. Here.
That's super interesting. So what we learned is that, yeah, you can tune a certain kernel for a certain ballpark. I mean, sometimes you can auto-tune kernels. You can have a bunch of them. And in fact, PyTorch has a bunch of kernels for the same ops that are more optimal in different ranges of things.
Well, yeah, if you count kublas for the linear, it's like hundreds, right?
Hundreds of kernels, exactly. So, there's no fast kernel, or there is, but in a certain range of things. And that was pretty dramatic here. It got very, very slow for short lengths, sequence lengths. And then
Yeah,
it stayed basically the same for much longer sequence lengths as PyTorch's kernel was getting slower, and then we got another out of memory on the other side.
right.
That's pretty
And
interesting.
so obviously great achievement if you want to have something with larger. And now we see that, yeah, it's a tad faster, but if you compare the percentages, it's like not that much, right? So 159 divided by 139 is
And that
14
memory usage will be very different.
slower. And obviously I can do this one here. I can bump this to 16 for Liger easily, but I can't for maybe I can if I don't have much else. But yeah, I'm getting out of memory here again.
Yep.
And so even though I think this is our process where we have all the memory in use, I'm going to double check here just to be sure. But obviously we saw, yeah, now it's down to 0 again. But even if we start from scratch, more or less, we have that this runs out of memory if we don't fuse the linear cross entropy, and it just survives when you do the Liger. And then obviously Liger thing is better to have if you have this kind of workload.
Yeah. Also, something that it was worth mentioning is that you can have chunked cross entropy computation. So the way we're doing it with PyTorch right now is kind of more naive because we just have the whole big cross entropy being computed in just one step. There's also the possibility of chunking cross entropy and breaking it down to multiple loss contributions, as we do in LibGPT, by the way. But of course, that means that it will take more time because you need to do it multiple times and then sum them up. So you're going to trade speed with compute, which is great. And so we learned a ton. I think that kind of concludes our journey into Liger. Maybe we can show the whole thing. I don't know. putting it all together with a final like notebook that everybody can use.
Right.
But I think, yeah, we learned a ton, and that was a great journey. We learned by doing, and
Yeah.
so, and we also learned that we have some shortcomings with the APIs and so on. So we need to fill them in, which is part of why we're doing this every week. Yeah.
Right. So super good. Thanks, Luca. And
Thank you. Go back to
you,
your last few hours of vacation and then into the
right.
weekend, and then we'll meet on Monday.
Right. You have a good weekend too. See you.
Yeah. Bye. See you, Thomas.